Welcome to Math 2320, Section 2.3 on linear equations. Linear equations have a general form that looks like the following. But often we put it in standard form where we have the derivative of y plus some function p of x times y equals f of x, our driving function on the right-hand side. Now it turns out that a technique to solve these linear equations is by using something called an integrating factor. And the integrating factor is of the form mu of x is e raised to the integral of that function p of x that was in front of the y. Now let's go back and look at that for a moment. Notice that that is on the left-hand side. So you get all the y's on the left. You identify this p as the function in front of the y. So it turns out that if you multiply this integrating factor all the way through, what you can recognize is that what that gives you on the left is the derivative of this particular product of your integrating factor times y. So you can integrate both sides and you can get your hands then on the solution of y as the integral of your integrating factor times your forcing function. And certainly you have to divide by whatever this is as well. So let's see how that plays out here in question 1. We have dy dx equals 7y. We could solve this by separating it, but we're going to solve it by this particular method. So the first thing I do is I move the 7y over to the left so I can identify that the minus 7 is my p of x. And so this is e integral of that. And so this is my integrating factor. Therefore, the left-hand side is recognizable as the derivative of that integrating factor times y and the integrating factor times the item on the right. Integrating both sides, well, the integral of 0 is 0 plus a constant. If I now divide both sides by e to the minus 7x, well, 0 doesn't matter, so I have c over e to the minus 7x. Well, if you think about that, how did I get from there to there? Well, c over e to the minus 7x is the same as c over 1 over e to the 7x. Therefore, you can flip this and it comes to the top, and this is c e to the 7x. E is defined for all real numbers. There's no discontinuities. It's continuous on the whole number line. And there are no transient terms, meaning any terms that go to 0 as x goes to infinity. All right, in question 2. Here's how it's given to us. So first off, I'm going to clean it up and divide all the way through by 4. All right, so we get this particular format. The minus 5 in the front of the y is my p of x. So my integrating factor is e to the 5x. Therefore, it's writable if you multiply through by your integrating factor. The derivative of this product. On the right, I've got 5/4 e to the 5x. So integrating, I need to integrate 5/4 e to the 5 5x. All right, so what happens? Well, the 5/4 is out in the front. Using substitution, you're going to pick up a 1/5. 1/5 times the 5/4, the 5's cancel, and so we get this. Dividing through now by e to the 5x. All right, these cancel. C over e to the 5x. This piece is writable as c e to the minus 5x. So all I've done there is c over e to the 5x is c times 1 over e to the 5x, and then simplify this as e to the minus 5x. So this is defined again for all real numbers. If you look at the limit as x goes to infinity, this is a e with a negative exponent, therefore it does decay to 0. It is the transient term, and so the long-time behavior of this differential equation is the solution will level off to 1/4. All right, in problem 3 here, I divide through by cosine. All right, I'm worried about that because I know cosine is 0 at some points. So let's see, when I do that, I get sine over cosine, which is tangent, and 1 over cosine, which is secant. All right, therefore, this is my p of x. So I'm integrating the tangent, which you can do by substitution or use your table of integrals. And I get minus ln, absolute value of the cosine. So I've got e raised to this minus ln. Now at this point we should remember that e to the ln of something would give it to me back. But this presents a problem. So what I'm going to do is take the minus back up onto the absolute value. And so this is e to the ln of 1 over the cosine. Well, now e to the ln of something, and I get that back, which is the absolute value of the secant. So I'm wondering now, what do I do with the absolute value? Well, let's see. We've got the tangent involved in our differential equation, and the tangent's only going to be defined between minus pi over 2 and pi over 2. Well, on that particular interval, secant is positive, so I don't need the absolute value of the secant, and so I can get rid of it, considering we're only solving this on this particular set of x's. So therefore, the left-hand side is, here's my integrating factor, is writable as this derivative of a product. On the right-hand side, I get secant squared. All right, well, what is the integral of secant squared? All right, well, integral of secant squared is tangent. So I've got tangent plus this c. Divide through by secant. Let's see, c over secant, that's a 1 over secant, which is a cosine. And if you simplify this, so I've got sine over cosine, 1 over cosine. 1 over cosine flips, and so I'm left with the sine. So the long-term behavior of this is it continues to oscillate. There are no transient terms or terms that would go to 0. All right, in question 4, we're looking at a problem from electrical engineering or from physics. So we have a circuit where we have an inductance, we have a resistor, we have a electromotive force here, E, and we have an initial current. All right, so we like to solve this particular system. L is constant, R is constant, E is constant. All right. So I divide through by L, and so I realize that this piece, R over L, is my P. So my integrating factor is E to the R over L times T. All right, multiplying this across. All right, integrating, let's see what happens when I integrate. Well, I get a E over L, that's here. If I integrate E to the something, I get 1 over R over L. That flips and I get L over R. The L's cancel. All right, so we are to this. At that point, I need to divide through by E to the R over LT. All right, so when I do that, well, what's going to happen? Well, this one will cancel that one, giving me E over R. I've got a C over this E. Well, that's E to the minus R over L. We have an initial current, all right, and I need to realize E to the 0 is 1. So when the time is 0, E to the 0 is 1. And so I get E over R plus C is my initial current, and I can solve for the constant. And so putting all that back in, what I see is I get this transient term. This is the term that's going to decay to 0 over time. And initially the current will stabilize to be constant as E over R. Now in our last problem here, we have a driving function f of x, which has a different behavior depending upon where the x is. F of x is either 1 or minus 1. All right, so looking at my driving function, it's 1 from 0 to 1, and then it flips to minus 1, open dot there, all the way forever, and this is at minus 1 plus 1. So here's my f of x. And so the way we solve this is parts 1 and 2. On the first part, we're solving this from 0 to 1. We use the behavior of f on that interval. And my initial condition is y at 0 is 1, which was given to us. On part 2, this is for x is greater than 1. The driving function is minus 1. The key here is what's my new initial condition? And my new initial condition at 1 is where the first solution ended. All right, so I need to solve this on part 1, which is fairly easy. My integrating factor is e to the x. I'm integrating e to the x, which is e to the x, and dividing through, I get y of x is 1 plus c e to the minus x. Our initial condition was y at 0 is 1, and so that gives me c is 0, and so I get y of x is the constant function 1 on the interval 0 to 1. So y of x just stays stuck at 1. So we talked about where the first function ended. So it ended right there. And so my new initial condition is y of 1 is 1. And so now I solve part 2 using that particular fact. Same integrating factor. Right hand side is a little different because of the minus 1. Otherwise, it's fairly easy to solve. So here's where my new initial condition is included. Y at 1 is 1, and so when I fill all that in, I figure out that C is 2 over e to the minus 1, which is just 2e. And if I plug that in, this is 2e to the 1. This is a 1 here. Multiplied by e to the minus x. The exponents add. That's how I got to there. And so y of x is 2e to the 1 minus x minus 1. And that's on the interval for x is bigger than 1. And so what you see is here was the solution to our first piece. It then decays over time. This is a transient term. As x goes to infinity, this particular piece goes to 0, which is what you're seeing here is the solution is decaying down to level off at minus 1.